Okay, let's unpack this. We are diving deep into something every engineer, hobbyist, and, fundamentally curious learner relies on, the printed circuit board, or PCB.
Hmm.
But we're going past the surface components and the schematic logic. We are looking at the architecture beneath, the very bedrock that dictates system reliability, the PCB stackup.
That's right. For anyone designing high-speed systems, the physical layer is, well, it's everything. The stack-up configuration is the foundation that directly influences the three critical performance domains: signal integrity, or SI,
Right.
power integrity, PI, and of course, electromagnetic compatibility, EMC. If the stack-up is flawed, you've pretty much guaranteed performance bottlenecks and some really expensive failure modes long before you even place the first component.
And our mission today, and we're drawing extensively from this analysis by Dario Fresu, tackles one of the most ingrained and potentially dangerous design habits in the industry:
I know exactly the one you mean.
the reliance on using power planes as the primary return path for high-speed signals. We really need to determine if this popular cost-saving technique is fundamentally incompatible with achieving, robust, predictable electromagnetic behavior.
It's an essential clarification for the modern design world.
Yeah.
I mean, when we push clock speeds into the hundreds of megahertz and beyond, physics takes over and convenience, well, it becomes secondary.
Definitely.
Our objective is to move beyond common assumptions and define a stack-up design philosophy, one that prioritizes continuous low-impedance return paths and avoids those common pitfalls that lead to board radiation and signal degradation. We need to understand why the current flows the way it does.
So let's establish those core principles first. We're calling this the invisible rules of current flow. Frequency is key. And it all starts with, I guess, the simplest rule in electrical engineering, but one that gets complex really fast: the circuit loop imperative.
It sounds obvious, but it's probably the most violated rule in high-speed design. The signal current, whether it's DC or high frequency, must always complete a circuit loop. It has to return to its source. The difference is how it chooses that return path.
Okay, so let's ground ourselves in the familiar first. How does current behave at really low frequencies, say below the kilohertz range? This is the stuff we all learned in our first physics class.
At low frequencies, we're mostly dealing with resistance, which is just the opposition to DC current flow. Low-frequency current is largely indifferent to electromagnetism. It simply follows the path of least resistance.
So it's just looking for the easiest, widest path back.
Exactly. Imagine a thick copper pore on your board. If you apply a low-frequency signal, the current will spread out widely across that entire conductive area, taking the shortest or widest path back to its source. It acts like a sort of diffuse fluid flow.
So if I have a 100 hertz signal on a trace, and beneath it I've got this massive ground plane, the return current doesn't necessarily hug the trace.
Not at all. It just uses the bulk conductivity of the entire plane. It's widely dispersed and often, unpredictable in its exact distribution across that area. It doesn't really rely on or interact strongly with the signal's own electromagnetic field. This model works perfectly for DC and audio frequencies.
But the moment we move into high-speed digital, anything above, 10 or 20 kilohertz, the behavior shifts dramatically and resistance becomes almost irrelevant. What's the fundamental change that dictates the current path now?
The change is driven by the rise of inductive and capacitive effects, which we combine into one word: impedance. At high frequencies, the current follows the path of least impedance, not just resistance.
Okay.
This means the electromagnetic forces generated by the signal trace itself now dominate the current's behavior.
And how does the current go about minimizing impedance?
It minimizes the inductive component of the impedance. And inductance is minimized by reducing the physical loop area formed by the forward signal path and the return path. So physics dictates that the return current is forced to concentrate in a very narrow path directly beneath the signal trace,
Even if there are other shorter DC paths available.
regardless of what other paths might exist. It's like the signal and its return current are magnetically inseparable, traveling as this tightly coupled pair.
That's a great way to visualize it.
And by minimizing that loop area, we accomplish two absolutely crucial electromagnetic goals. First, we achieve the lowest possible loop inductance, which is essential for maintaining the characteristic impedance of the transmission line.
Right. If the path widens, the impedance changes and you get reflections.
Precisely. And second, and this is equally important, this tight coupling confines the electromagnetic fields.
Confinement being the key to avoiding radiation.
Absolutely. When the forward and return currents flow closely parallel, they create electromagnetic fields that are equal in magnitude, but opposite in direction. Outside of the immediate area of the trace, these fields largely cancel each other out.
So less leakage, less noise.
Minimal leakage, minimal coupling to neighboring traces, and minimal radiation. This tightly coupled return path is a bedrock of good signal integrity and low electromagnetic interference.
So the faster the signal, the more critical it is that we provide this clean, contiguous path right underneath the trace. And if that path is broken, the loop expands, the magnetic field containment fails, and we've inadvertently designed an antenna.
You've just designed an antenna, exactly. And that understanding of the path of least impedance brings us right up against the limitations of some very common design practices.
Which moves us smoothly into Section 2, limitations of the standard 4-layer stackup. This configuration is, it's everywhere. Why is that?
The typical configuration, the one that's really the target of this critique, stacks up like this. You have a signal layer on top, then a power plane, or PWR, then a return reference plane, RRP, which is usually ground, and then another signal layer on the bottom.
And it's so popular because it's cheap, right? It's the standard.
It's the cheapest, most standard arrangement offered by pretty much any fabrication house.
And the designer makes a seemingly logical assumption when using the stackup, I'm guessing.
They do. The assumption is that the outer signal traces can reference the adjacent internal plane, even if that adjacent plane is VCC, or power. So the top signal references the power plane, and the bottom signal references the ground plane.
That seems practical, I guess. You get big copper areas for power and a single ground reference.
It seems practical. But this is where we need to introduce some intellectual tension. Designers have been using 4-layer boards for decades. If referencing a power plane is so fundamentally flawed for high-speed signals, why hasn't the industry just universally abandoned this configuration?
That's a really good question. There has to be a reason it persists.
There is. And the reason lies in the genuine, undeniable benefit this setup provides for power integrity, which we absolutely have to acknowledge, and that is interplane capacitance.
Okay, let's dive into that. A thin layer of dielectric separating the large parallel power and ground planes. That creates a giant capacitor. Why is that so good for power delivery?
Because it fundamentally lowers the impedance of the power distribution network, the PDN. If you think back to the impedance formula for a capacitor, Z equals 1 over J omega C, a large distributed capacitance means very low impedance across a really wide frequency spectrum.
And that's critical for transient power.
It's crucial. When an integrated circuit switches state, which can happen in picoseconds, it demands a massive, instantaneous surge of current.
So this is like a localized, high-frequency energy reservoir right where the chip needs it.
That's the perfect description. This distributed charge reservoir stabilizes the voltage rails by supplying that transient current faster and more efficiently than discrete decoupling capacitors alone can manage. For the goal of power integrity, this parallel plane arrangement is fantastic.
So it's not all bad.
For PI, it genuinely enhances power delivery and minimizes low-frequency power ripple. This benefit, as the source material stresses, is not the problem.
But now we move from the power domain to the signal domain. We have this beautiful PI structure, but the moment we use one of those planes, say VCC, as the reference for our high-speed signals, that's when the signal integrity and EMC advantages just rapidly erode.
The problem arises because signal propagation is driven by electromagnetic fields, and these fields are entirely dependent on having a continuous low-impedance path. When that path crosses the boundary between two planes at different DC potentials, VCC and ground, the physics of the return current is, well, it's thrown into chaos.
And that takes us right to the heart of the matter. Section 3, the problem of the split potential return path.
This is the core disconnect. Let's assume our top signal trace is running at, say, 1 gigahertz, and it's referencing the adjacent VCC plane. The return current needs to flow directly beneath that trace, confined to that narrow path.
But its ultimate destination is the source driver, which is on the ground plane.
Right. So the high-frequency return current can't just jump across the VCC plane and connect to the ground plane anywhere at once. They are separated by the operating voltage.
They're only connected at specific points through decoupling caps and things like that.
Exactly. So the return current is faced with two inherently suboptimal high-impedance paths to bridge that DC potential difference. And neither path is ideal for a clean, confined return.
Okay, so let's look at the first path, which is maybe the most invisible and confusing one. Displacement current through the dielectric. How does this actually happen?
Okay, think of the dielectric between the planes as the insulator in a capacitor. When the high-speed signal trace is excited, It creates these rapidly changing electromagnetic fields, or E fields, that try to cross the dielectric gap from the VCC plane to the ground plane.
So it's not electrons physically crossing.
No, instead of electrons physically traversing the gap, which would be conductive current, the energy of the current loop is maintained by the movement of the electromagnetic field itself. That mechanism is called displacement current.
So the return current path is maintained locally, right under the trace, but the energy is being transferred through the insulating material.
Yes. And this path keeps the loop area small, which is good for signal integrity locally. However, transferring energy this way introduces a pretty significant side effect.
Which is?
The displacement current causes rapid voltage fluctuations, or dVdt, between the VCC and RRP planes in that local area. You're essentially charging and discharging the capacitor formed by the planes with every single transition of the signal.
And those voltage drops are noise injected right into the critical power distribution network.
Exactly. Even though the return path is local, it comes at the cost of polluting the power rails. And that fluctuation is extremely dangerous, especially for sensitive components that might be nearby.
Okay, that's path 1. Low inductance loop, but noisy power rails. What about path 2? The path we usually try to rely on, the conductive path, via decoupling capacitors.
This is the path where the return current travels conductively across the VCC plane until it finds the nearest physical decoupling capacitor that connects VCC to ground. It has to pass through that component and then continue its journey on the ground plane.
The moment the current has to travel across the plane to find a capacitor, that elegant, tight electromagnetic coupling is just destroyed, isn't it?
Absolutely. The loop area suddenly expands to encompass that entire physical detour, from beneath the trace, across the plane, through the capacitor, and then back onto the RRP. This creates a physically larger current loop, which exponentially increases the loop inductance.
And as we established earlier, higher inductance means the board becomes a more efficient antenna, more radiation, more signal degradation.
You got it. So we're stuck between a rock and a hard place. Either we tolerate noise injection through displacement current, or we create a massive radiating loop through the conductive path. It's a fundamental structural dilemma.
It's a lose-lose situation.
It truly is, and it gets even worse when we look closer at path 2 and hit the unavoidable reality of the capacitor impedance wall. This is a key aha moment for designers moving from low-speed to high-speed logic.
Decoupling capacitors are not ideal connectors across high-frequency nets. Is that the issue?
Not at all. Every real-world capacitor contains parasitic internal inductance. This defines the capacitor's self-resonant frequency, or SRF. Below the SRF, the component behaves as you'd expect. Low impedance, offering a good bridge.
But above the SRF?
Above the SRF, that parasitic conductance dominates the component's behavior.
Yeah.
The impedance skyrockets, and the capacitor effectively functions as a high-impedance inductor.
Wow. So if I'm routing a high-speed signal, let's say a 1 gigahertz clock, and I'm relying on a standard 0.1 microfarad ceramic capacitor whose SRF might only be, 200 megahertz?
Then for 80% of your signal energy, that conductive return path no longer exists.
The capacitor bridge just collapses.
It collapses. At those higher frequencies, the conductive path through the components closes, forcing the majority of the return current even more heavily into that undesirable displacement current path.
Which then intensifies the voltage fluctuations, the power bounce, and dramatically escalates the EMI risks we talked about. The higher the frequency, the faster your caps expire, and the more violently the system radiates.
The takeaway is that this common stackup forces you to rely on frequency-limited components, capacitors, to solve a fundamental physics problem, the DC potential difference. It pretty much guarantees failure at higher speeds.
And that structural weakness is then compounded by common layout practices, bringing us to Section 4, design discontinuities and their antenna effect. We rarely run systems on a single voltage.
That's the reality. You need multiple voltage domains, 3.3V, 1.8V, 1.2V, meaning the power plane, if you're using one, has to be segmented or split into separate regions. These splits are the second critical point of failure in this kind of stackup.
And if a high-speed signal trace accidentally routes across one of those power plane splits, the consequences are immediate and severe. Our sources highlight 4 major cascading problems. Let's start with impedance discontinuity.
Okay, so maintaining a stable characteristic impedance, typically 50 ohms, requires a stable continuous reference directly beneath the trace. The moment that trace crosses the split, the solid copper reference just vanishes. It's replaced by a gap of dielectric material or air.
What does that do to the signal itself at that point?
The instantaneous impedance of the transmission line changes dramatically. It either spikes or it drops because the geometry is suddenly changed. This abrupt change acts like a physical barrier to the high-frequency wavefront. A portion of the signal energy is reflected back down the trace toward the source.
Causing ringing, timing problems, the works.
Signal degradation, timing distortion, and ultimately loss of data integrity. You hit a reflection wall.
So that's one. The second related problem is the return path disruption.
As soon as the signal crosses the split, the high-frequency return current, which needs to flow right beneath the trace, finds itself completely blocked. There's no continuity. So it's forced to take this long, ugly detour, traveling laterally to find the nearest point where the two separate power regions are bridged.
Which is usually a decoupling cap located far away.
Exactly. And as we just discussed, that long detour results in a massive increase in loop inductance. The return path becomes high inductance, unpredictable, and entirely dependent on those frequency-limited components. This is why strict design rules often forbid routing high-speed signals over any plane split, even by a millimeter. The consequences are catastrophic.
Now let's talk about the gap itself. It's not just blocking the current. The physical split is transforming into a slot antenna formation.
This is a classic EMC failure mechanism. When the high-frequency return current is forced to flow along the edges of that split, you can picture the current concentrating and moving around the obstacle. It excites the physical gap structure. This gap, which is basically a long, narrow aperture in a conductive plane, becomes an extremely effective antenna.
Is there a relationship between the size of that split and the frequencies it radiates?
Oh, absolutely. The length of that physical slot is directly related to the wavelength of the frequencies it will radiate most efficiently. If you have a split that is, say, half an inch long, that length is proportional to the half wavelength of the noise it will broadcast most effectively. An inch-long split can radiate dangerously efficient noise in the low gigahertz range.
You've just built a highly optimized RF radiator right where you wanted clean signal confinement.
It's a compliance killer, a terrifying consequence. Which brings us to the final problem with these splits: amplified crosstalk and coupling.
How does that happen?
If you have multiple signals crossing the same split region, they are all vying for the same convoluted return path. They're all forced to share the same small, high-inductance conductive bridge, that bank of decoupling capacitors. Because their return paths are intertwined and noisy, the electromagnetic fields are no longer confined and separated.
They start bleeding into each other.
Exactly. This increases noise coupling and crosstalk dramatically, as the signals are essentially fighting for the same congested return route.
So these structural defects don't just degrade the signal that crossed the split, they pollute the entire reference system. This leads us directly to understanding the common mode current risk. What makes common mode currents so much more dangerous than the desired differential mode currents?
This distinction is crucial for understanding why boards fail EMC tests. Differential mode current is the good stuff. The forward current and the return current travel in opposite directions, and their magnetic fields cancel each other out. That confinement is what keeps radiation minimal.
Like the opposite magnetic fields we talked about earlier, they neutralize the effect outside their tight loop.
Exactly. Common mode currents, on the other hand, are the result of noise, a voltage differential being generated within the reference plane system itself, often from these return path discontinuities like splits or poor via transitions. When the return path impedance is high, the cancellation fails.
And they flow in the same direction.
They flow in the same direction relative to a distant large reference, like the metal case, the chassis, or the attached cable shields. Because they flow in the same direction, their fields don't cancel, they add up.
Which means they act as highly efficient antennas.
Very efficient. When designers run into EMC compliance problems, failing those mandatory certification tests, it is almost always traced back to uncontrolled common mode currents generated by these layout flaws. Managing the return path impedance is fundamentally about suppressing the generation of common mode noise.
It sounds like the moment we introduce a voltage differential between the signal reference plane and the true circuit return path, we're just asking for trouble. Let's move to another classic complexity: vertical transitions, covered in Section 5. The via transition and cavity resonance. What happens when a signal changes layers using a via, specifically when it's referencing a power plane?
When a high-speed signal transitions from, say, layer 1 to layer 4, the return current has to transition layers too. If layer 1 references VCC and layer 4 references ground, the problem immediately resurfaces. The return current cannot simply follow the signal via because the VCC and ground planes are at different DC potentials.
So the current is blocked vertically, just like it was horizontally at the split.
It is. It's forced into the same suboptimal detours, either traveling laterally across the plane to find a distant decoupling capacitor or crossing the dielectric as displacement current. Both paths significantly increase the loop inductance associated with that via transition. You've just created a localized noise source and a radiation point right there on the board.
And that's the local problem. But the interaction between the parallel planes creates a bigger structural issue known as electromagnetic cavity resonance.
This is a complex but really crucial concept. Any pair of large parallel conductive structures, like a power plane and a ground plane, forms what's essentially a parallel plate transmission line, or an electromagnetic cavity, separated by the dielectric.
Like an organ pipe or a sound box, it can trap energy.
Exactly like that. If a poorly designed via transition one that references VCC injects high-frequency signal energy into this cavity, and if the signal frequency happens to match one of the cavity's natural resonant modes, that energy gets trapped and amplifies dramatically.
And what's the result of that amplification?
Massive standing wave disturbances. You're injecting noise into both the power rails and radiating noise outward. It affects SI and PI simultaneously and can often cripple the entire system performance over specific frequency bands.
So a localized noise source becomes a system-wide noise source, amplified by the board structure itself. Let's circle back to that displacement current flow in this context.
Right. The displacement current flowing through the dielectric between the power and ground planes isn't narrowly confined like conductive current in a trace. It tends to spread out over a much larger area. This spreading of fluctuating electromagnetic fields creates a sort of a zone of influence around that via transition.
And if any other vias from completely unrelated nets pass through this fluctuating zone,
They're susceptible to coupling. If vias from slow clocks or reset lines or even sensitive analog grounds pass through this large region of dynamically changing fields, they can easily pick up these voltage fluctuations.
and this coupling manifests as what?
Localized ground bounce or power bounce. The local DC reference level in those unrelated nets shifts momentarily because of this shared noisy return mechanism. It's a critical form of crosstalk, especially lethal in low noise budget circuits where stability is everything.
It really sounds like the power plane as reference pairing is just architecturally unsound for high-speed signals.
It creates unnecessary and unpredictable complications at every single layer transition and horizontal split. Now let's contrast this with the elegant solution proposed in the source material, a stackup that uses two return reference planes, two RRPs.
The favorable scenario. Why does simply swapping a power plane for a second ground plane solve so many of these problems?
Because the two RRPs are fundamentally at the same DC potential. They're both ground. This restores control and predictability. And the crucial element this enables is the use of stitching vias.
Okay, explain how stitching vias neutralize that via transition problem.
A stitching via is just a via that connects RRP1 on, say, layer 2 to RRP2 on layer 3. When your signal transitions from the top layer, which references RRP1, to the bottom layer, which references RRP2, you place a stitching via right next to the signal via.
I see.
Because both planes are ground, the return current can seamlessly jump from RRP1 to RRP2 through that nearby stitching via.
So it's like you're building a tiny, perfect bridge for the return current to follow the signal. It keeps the loop area extremely small, wrapping the return current tightly around the signal path, even through the transition.
That's a perfect way to put it. It minimizes loop inductance, it maintains continuity, and it contains the signal energy entirely within the RRP layers. Furthermore, by densely connecting the RRPs across the board with lots of stitching vias, the size of that unwanted electromagnetic cavity is dramatically reduced.
And reducing the cavity size pushes the resonant frequency far higher.
Potentially out of the range of the active signals that could excite it, making the structure far more electromagnetically stable. It is the ultimate form of electromagnetic control and containment.
And you just can't do this with a power ground pair.
You simply cannot use stitching vias with PWR-RRP pairs because of the voltage difference. You're forced back to relying on those frequency-limited decoupling capacitors, which can only partially and temporarily bridge the gap, leaving the system highly susceptible to noise and resonance.
This deep dive really does advocate for a complete philosophical shift, prioritizing the continuity of the return path over the convenience of a dedicated power plane.
Which brings us to Section 6, the recommended stackup philosophy. The foundational principle is based on electromagnetic science, not on cost. paired layers.
Meaning every signal layer must be placed immediately adjacent to a dedicated return and reference plane, an RRP.
Yes. The electromagnetic field for that signal is then channeled and contained within the dielectric between the two, using the RRP as its local continuous return path.
So what's the optimal four-layer recommendation?
The robust alternative is signal on top, then RRP1, which is ground, then RRP2, which is also ground, and finally signal on the bottom. The two central layers are solid interconnected equipotential reference planes.
That is the crucial modification. But this raises the most pragmatic question from a designer. How do we distribute power if we eliminate the large power plane? Power delivery is still essential.
Of course. In this recommended Stackup, power distribution is handled using properly sized traces, not planes. For the vast majority of four-layer boards, microcontrollers, standard digital buses, interfaces, the current demands are actually quite modest.
We need to separate the requirements for high-speed electromagnetic flow from the needs of steady-state DC current delivery.
Exactly. You design the power traces for sufficient current carrying capacity and thermal management. Those are DC and thermal considerations, not signal integrity concerns. You use trace width and copper weight calculations to ensure that the voltage drop is acceptable and that the trace doesn't overheat.
And this approach avoids all those complex high-frequency issues.
It does. It frees up the two internal layers to serve their highest purpose, providing a stable, equipotential, continuous signal reference.
So let's just summarize the undeniable advantages this recommended SRRP-RRPS Stackup delivers.
Okay, firstly, consistent low inductance return paths. The loop area is minimized, giving you maximum signal integrity and minimal external field leakage.
And then the channeling of fields?
Secondly, effective channeling of fields, confining the electromagnetic energy within the dielectrics adjacent to the RRPs. Thirdly, and this is a big one, you gain the ability to use stitching vias, which ensures RRP1 and RP2 are equipotential, guaranteeing smooth, low-noise transitions when signals change layers.
That capability alone seems to justify the change.
It does. And finally, and most important for production and compliance, you get lower emissions and significantly reduced common mode current generation because the return path impedance is inherently lower, more controlled, and continuous.
So the engineering decision is fundamentally shifted. Instead of engineering workarounds to manage a compromised structure, we are optimizing the structure itself for clean electromagnetic flow.
That is the core philosophical takeaway. You minimize the problem at the physical foundation. However, we have to provide balance. We did establish earlier that the power plane approach is sometimes necessary.
Right. So under what specific limiting criteria does the source material justify the complexity and risk of using a traditional power plane?
There are really only two primary justifications. The first is extreme, actual current demands. If you're dealing with specialized power electronics or industrial applications requiring current delivery well over, say, 100 amps, a simple thick trace might be physically inadequate to manage the current density and the thermal rise.
So in those rare cases, you need the bulk conductivity of a plane.
You need the bulk conductivity and the heat dissipation capacity. The second justification relates back to that PI benefit we acknowledged earlier, the power distribution network.
So extreme PDN target impedance needs.
Precisely. For state-of-the-art, high-frequency processors, large FPGAs, or complex ASICs where core voltages are incredibly low, like 1.0 V, and instantaneous current transients are massive, the required target impedance for the PDN might be sub-milliohm across a huge frequency spectrum.
And to get there, you need that huge interplane capacitance.
You need the maximal distributed interplane capacitance that only large, closely spaced power and ground planes can provide.
But for the vast majority of standard digital and mixed signal boards, that extreme current demand or ultra-low PDN impedance target simply doesn't exist.
Correct. For most everyday four-layer designs, the analysis concludes that a robust, well-routed power distribution network using appropriately sized, thick traces combined with an effective, localized decoupling capacitor strategy delivers more than enough power performance. And it does it without incurring the catastrophic signal integrity and EMC risks inherent in referencing a split potential plane. You gain predictability and reliability.
The complexity here is astonishing, but the lessons are really clear. Let's make sure we distill this down to the actionable steps for the listener.
Okay. For you, the learner, the core lesson is to respect the high-frequency physics. While interplane capacitance is great for power integrity, using power planes as the signal reference introduces fundamental electromagnetic liabilities. Return path discontinuities, high inductive loops, dangerous cavity resonances, and a significantly elevated EMI risk. The minute your signal energy exceeds the SRF capability of your decoupling capacitors, you lose control.
Therefore, the crucial takeaway is that for most common four-layer designs, opting for two dedicated return reference planes, relying on stitching biased vias to maintain equipotentiality, and distributing power through properly sized traces yields superior, more predictable electromagnetic behavior. You're prioritizing the continuity of the electromagnetic field over the simplification of the power net layout.
And the result is lower design risk, higher signal quality, and a dramatically reduced chance of costly and time-consuming compliance failures.
So we've focused heavily on the geometry and the connectivity of the copper layers, making the return path continuous and low impedance using stitching vias. But if we assume we've solved the geometric problems with the recommended stackup, what becomes the next frontier for optimization?
That continuous path is the first step, but remember that high-speed return current follows the path of least impedance, and that path is essentially defined by the dielectric material separating the signal trace from the RRP.
Right, the displacement current, which carries the energy, flows through that material.
Precisely. As signals push into the high gigahertz range, the electrical properties of the material itself become the new constraint. The dielectric constant affects signal velocity and impedance, and the loss tangent dictates how much energy is dissipated as heat. Even with a perfect copper stackup, if your dielectric material is lossy or introduces unnecessary delay, your signal performance is going to suffer.
So, if the stackup geometry is now optimized and predictable, the next step isn't how to route the signal, but what material to embed it in, especially when you're dealing with ultra-high-speed signaling like PCIe Gen 4 or Gen 5.
That is the provocative thought we leave you with. If we minimize the geometric inductance and eliminate discontinuities using the recommended RRP stackup, the critical variable shifts to the intrinsic material properties, the precise characteristics that govern displacement, current flow, and signal velocity. How does the choice between standard FR4 and a low-loss material like PTFE become the primary decision point for optimizing signal integrity and mitigating losses in your next high-speed design? Think materials, not just metal.